Hello, my name is Diane, and I'm going to be talking about introduction to machine learning. Machine learning is a field of study that enables computers to learn from data and identify patterns without being explicitly programmed. It is based on the idea that a system is able to learn from the data, identify patterns, and then make some decisions with a minimal amount of interventions from humans. Therefore, the more exposure the system has to more data, the more enhanced its performance is on a task. There are several types of machine learning, but we can broadly categorize them into two main types, which is supervised learning and unsupervised learning. Supervised learning involves training models on unlabeled datasets to make predictions on unseen data, and it primarily consists of two types, which is regression and classification. In regression, the goal involves predicting a continuous numerical value based on one or more input features. Some applications are stock market prices or house prices given different features like number of bedrooms, location, etc. Whereas in classification, the goal is to predict a categorical label for a given input or inputs. Therefore, each input is assigned a specific category or class. For example, spam detection. So, for example, some applications include email spam detection or image classification. In unsupervised learning, the model is trained on data that is not labeled and must find patterns and relationships. In unsupervised learning, the model is trained on data that is not labeled and must find patterns and relationships in the data on its own. And its key types include clustering, in which the goal is to group similar data points together based on their features, for example, grouping customers based on their purchasing behaviors. And then the other type is anomaly detection, which involves identification of unusual or rare observations in the data that do not conform to the expected patterns, and and this is applied in fraud detection or network intrusion. To note, there are other types of machine learning, such as semi-supervised learning, reinforcement learning, self-supervised learning, each with its own unique applications and methodologies. Moving on to end-to-end machine learning, it is a concept in the field of artificial intelligence whereby a system learns to perform a specific task without relying on intermediate stages of processing or feature engineering. It focuses mainly on the end-to-end machine learning pipeline, which covers all steps involved in building, deploying, and maintaining machine learning models. The The machine learning pipeline steps include data collection, data cleaning, data processing, feature engineering, model selection, model training, model evaluation, hyperparameter tuning, model deployment, and maintenance. Moving on to exploratory data analysis, EDA, and feature scaling. EDA is a process of visual and statistical exploration of datasets to summarize their main characteristics, usually with the help of graphical representation. EDA is typically applied in the data preparation phase of machine learning pipeline with a focus on data cleaning and feature engineering. EDA is performed on clean data following the end-to-end machine learning pipeline. This process helps to comprehend the distribution of variables, relationships between variables, and find out patterns and anomalies. Relevant features based on the insights gained from EDA are then extracted and created to prepare for data modeling. On the other hand, feature scaling is the process in end-to-end machine learning that involves transforming numerical features of a dataset to a similar scale. It is necessary because machine learning algorithms are sensitive to the scale of features. For example, if one feature has a larger range, it dominates the model, leading to biased results, poor performance, and difficulty in model interpretation. Common types Common types of feature scaling include standardization, normalization, and in standardization, it includes subtracting the mean and dividing by the standard deviation, while normalization, which is also known as min-max scaling, which is scaling the features to a fixed range. Others include log scaling and robust scaling. Moving on to linear and logistical regression. Linear regression is a linear model that predicts a continuous output variable based on one or more input features. The equation can be expressed as y equals to beta 0 plus beta 1 plus epsilon. And in that equation, y is a continuous output variable, x is the input feature, beta 0 is the intercept or the bias term, beta 1 is the slope coefficient, and the epsilon is the error term, which represents a random variation in the data. There are different types of linear regression, including simple linear regression, multiple linear regression, and multivariate linear regression. The key assumptions include linearity, which states that the relationship between the independent variables and the dependent variable is linear. This means that the change in the dependent variable is proportional to the change in the independent variable. Another key assumption is independence, which says that each observation is independent of the others, and the next one is homoscedasticity, which states that the variance of the errors is constant across all levels of independent variables. And lastly, normality of errors, which states that the errors are normally distributed. Moving on to logistic regression, it is used for binary classification. It models the probability of a binary outcome based on predictor variables. The equation is given below. The equation is seen on the screen, whereby P is the probability of the positive class and is the base of the natural logarithm, and Z is a linear combination of the input features. The assumptions for logistic regression include having a binary dependent variable. That is, the dependent variable should be binary, meaning it has only two possible outcomes. The independence of observations is another assumption, whereby each observation should be independent of others, and no multicollinearity. And no multicollinearity among predictors, which means that two or more variables in a regression model are highly correlated with each other. Common use cases involve predicting binary outcomes, such as whether an email is a spam or not. Moving on to KNN algorithm, which is k-nearest neighbors algorithm. This is a supervised machine learning algorithm used for both classification and regression tasks. KNN operates on the principle of feature similarity to predict outcomes based on closest training examples in the feature space. The parameters in KNN include K, which is the number of neighbors, and this determines how many neighbors to consider when making predictions. Distance metrics, commonly used metrics include Euclidean distance, Manhattan distance, and Hamming distance. Weighting schemes, options include uniform weighting, where all neighbors contribute equally, or distance-based weighting, where closer neighbors have greater influence. The advantages of KNN include its simplicity and ease of understanding, as well as the fact that it does not require a training phase. Predictions are made based on the entire dataset. However, it also has disadvantages, such as being computationally expensive with large datasets and being sensitive to irrelevant features and the choice of key. Implementation involves KNN implementation involves loading data, calculating distances, sorting distances, selecting neighbors, and assigning classes. When you look at visualization, we use scatter plots to visualize data points and their classifications. Dimensionality reduction techniques such as principal component analysis can help visualize high dimensional data in 2-dimension or 3-dimension. However, KNN performance can degrade with high-dimensional data due to the curse of dimensionality, which is a phenomenon that occurs when the feature space becomes sparse, making it difficult for the algorithm to find meaningful patterns. Therefore, to mitigate this, feature scaling, whether through normalization or standardization, is essential for effective distance calculations. Now we can explore the concept of entropy, which is a measure of impurity or disorder in a dataset, quantifying the uncertainty in predicting the class of a data point. And its formula is as seen on the screen, whereby hx is the Shannon entropy of a random variable x, and p in brackets x is the probability mass function of x, and the sum is taken over all possible values of x. Information gain reduces the reduction in entropy after a dataset is split on an attribute, indicating how effective an attribute is in classifying the data. The formula of information gain is I into brackets xy, which equals to x into brackets y minus h. The formula for information gain is Ig into brackets xy. is equals to h into brackets y minus h into brackets y given x, whereby ig xy is the information gained over feature x with respect to the target variable y. H into brackets y is the Shannon entropy of the target variable y, and h into brackets y given x is a conditional entropy of target variable y given feature x. Moving on to decision trees, there are tree-like modules used for classification and regression, splitting data into subsets based on feature values. The implementation steps include calculating entropy for the dataset, computing information gained for each attribute, and selecting the attribute with the highest information gained for the split. The process is repeated recursively until stopping criteria are met, such as maximum depth or maximum samples. To enhance decision trees, we use pruning, which involves removing branches from the tree to reduce complexity and prevent outfitting. There are two types. Which is pre-pruning and post-pruning, where pre-pruning stops the tree growth early based on certain criteria, while post-pruning removes branches after the tree is fully developed based on validation data. And finally, the gain ratio is the modification of information gain that accounts for the number of branches created by splitting an attribute, helping to avoid bias towards attributes with many values. The formula for gain ratio is on the screen, whereby gain ratio into bracket xy is the gain ratio of feature x with respect to target y, and the information gain into bracket xy is the information gain of feature x with respect to target y, and then intrinsic value into bracket x is the intrinsic value of feature x, also known as the entropy of feature x. Thank you.
Good evening, sir. My name is Karungi Maria Daphine from Year 2 Computer Science, and I'll take you through the last 3 modules of the diploma course, which is module 5, 6, and 7. So module 5 is about ensemble learning, which involves combining many mediocre models into one super model. It has 2 techniques mostly. There is bagging and there is boosting. Now for bagging, it's the same as aggregate bootstrapping, which is the idea of creating different models using different bootstrapped training sets and average their prediction to produce the final output of the model. For example, you have a set that contains values 1, 2, 3, and 4. Those are 4 values. So you generate different sets with the same amount of values as the original set. They can be 10 or even 20, but with the same amount of elements as the original set. And these elements, these sets contain random elements, and there's replacement. So you can replace the elements there. For example, set 1 can have 1, 2, 2, 4. Set 2 can have 1, 1, 3, 4. So you can repeat some elements also. Then why bagging? To reduce variance and overfitting and to reduce the chance of outliers. So the steps in bagging are mainly 3. Second, generate these different bootstrapped sets, then train these machine learning models on these sets, and finally get the prediction average of the output. So, as I said earlier on, you get different sets from the original set that you want to sample. Then you train these sets based on the model you want to use on them. Then finally you get their prediction average, or mean, for the final prediction. Then the out of bag error. For example, out of bag basically means that you have a set of 1, 2, 3, and 4, and you pick out, let me say, you pick out 1, 2, 2, 3. So out of bag will be 4 because you've left out 4. So that's what out of bag means. The ones that you've left out from what you've picked out. So mean prediction error on each training sample X using a model that did not have X in their training set, as I explained before, out of bag error. So boosting, which is sequential tree growing with weighted samples. So bagging is kind of parallel, then boosting is sequential. So boosting has other boosts, that's adaptive boosting, which uses decision stamps as weak learners, assigns weights to samples based on errors, then combines learners using weighted majority voting. How boosting works is that you train a weak learner, then you identify errors, you weight the errors, train the next model, then combine the models, repeat until errors are minimized. So random forests. about them, they are modified backing algorithms as well as collection of decorrelated decision trees. For every tree, we subsample the examples with placement bootstrapping. Then for each sample, we choose the attributes at random. Then we build the tree only on these random features. Then you classify the tree by taking a majority vote of the classification yielded. Then the pros and cons. The pros are robust to outliers, works well with nonlinear data, that's lower risk of overfitting, and runs efficiently on a large set of data. Then the cons are slow training, not suitable for linear methods, best while dealing with categorical data, and greedy algorithm doesn't yield the optimum tree structure. So the pros are same number as the cons. They want support vector machine, SVM. So SVM is a supervised learning algorithm used for classification and regression. It divides data into classes by finding the optimal hyperplane with the widest margin between classes. The key concepts in SVM is the hyperplane, the margin, and the support vectors. Now, let's say you have two scoops of ice cream, strawberry and vanilla, and you want to separate them from each other, the different flavors. So that space between those two scoops of ice cream, that's what we call a hyperplane. So hyperplane is a decision boundary separating classes. In the margin, the distance between the hyperplane and the closest data points, e.g. hard and soft margins. In support vectors, data point closest to the hyperplane. Then linear SVM works when data is linearly separable. For example, let's say you have a graph, and that graph has different points that you've plotted. Now, if you can easily draw a line between those two to separate, let me say, data points A from the data points B easily, without any hardship. So that's a linear SVM. So it's easily separable linearly. Linear is means a line, so you can easily draw a line between those different points. Then nonlinear SVM uses scalar functions, for example, Gaussian radial basis function, polynomial, sigmoid, cosine similarity kernel to map input data into higher dimensions for separation, and is used when data is not linearly separable. So for nonlinear, as it's explained itself, nonlinear, you can't really draw a line between the data points, so they're not really separable easily. So we use kernel functions that map input data into higher dimensions for separation. Then more about SVM. We have key parameters in SVM. We have the C and we have the gamma. Then the standardization, the pre-processing technique that transforms features to have a mean of 0 and a younger division of 1. Applications can be used in SVM, in PCA, in K-means, and it also ensures that all features contribute equally to the model and prevents certain features from dominating due to their scale. Then next to module 6, that's principal component analysis, that's PCA. It's unsupervised dimensionality reduction technique used to simplify large sets of data while preserving the most important information, the variance. So the key idea here is to basically project data into a lower dimensional space by finding new axes that capture the maximum variance. And the goal of this is to reduce the dimensionality of the data while keeping the information loss to a minimum. How PCA works is that there are 4 steps. The first step is standardize the data set, then you compute the covariance matrix, then you find Eugene values and Eugene vectors of the covariance matrix, then you project the data onto the top K Eugene vectors. Then more about PCA can be applied in image compression, in data visualization, facial recognition using Eugene faces, then in pre-processing step for classification tasks, then the add mutagen because we have them here, which is making computation faster, removes uncorrelated features, helps visualize high dimensional data. Then it can lose interpretability, then sensitive to scaling. Those are the advantages of PCA. Thank you very much.